Hello and welcome to another video lecture for CV in 2320 Differential Equations for Civil Engineers. This is Venki Ramay. In today's lecture, I'm going to be talking to you about finite difference approach for solving boundary value ordinary differential equations. As an outline, we will first discuss what boundary value problems are. Then I'm going to talk to you about the finite difference approach and show you how to write first and second order derivatives using the finite difference approach. And using the finite difference approach, we transform the ordinary differential equation into a system of linear equations. And we will see how that can be systematically derived, starting with an ODE and some assumptions. And finally, I'm going to show you how to solve the resulting system of linear equations, which essentially boils down to solving boundary value at discrete locations. And I'm going to wrap this all up using an illustrative example. So let's jump in and see how this is all done. Finite difference methods essentially transform a derivative into an algebraic expression. So the idea is to take a differential equation that we want to solve and turn it into something that is a system of algebraic equations that are hopefully easier to solve than the differential equation itself. So by solving the linear system of equations, algebraic equations, we end up getting a solution for our original differential equation that we solved. So what I'm showing here in this figure is a domain. So this you can think of as being your delta x or delta y. And clearly for differential equations, this domain is going to be continuous. In other words, x varies uniformly from some condition, from some starting point to some ending point, and your function is continuous in that point. So what we do in finite differences is that we essentially discretize this domain. And what we mean by that is we are going to take the domain of interest to us and then essentially pick several points of interest at which we are going to do our calculation. So these points of interest are also called nodes. And for simplicity, what we do is we space these nodes equally apart. So, and then here, I'm saying that delta x is the distance between two nodes. So from the center of this node to the center of that node, the distance is delta x, and that's the same between any two nodes we have. In an initial value problem, we have, for a second order ordinary differential equations, we saw that we need two initial conditions. We specify both those initial conditions at our inlet, and we typically we specify the value y, or the value of our state variable, and also the derivative of y at that same location, our inlet location. In a boundary value problem, we specify two conditions, but we specify them at two different points, one at the inlet and one at the outlet. So one at the beginning of our domain, one at the end of our domain. And we can specify a value of our state variable y here and specify the slope here, or we can specify the slope here and the value, or we can use a combination of both in terms of fluxes and specify them at both locations. So there are multiple different options in which we can specify those boundary conditions. Of course, we're not going to call them initial conditions here because they're not set at our inlet node or our first node. Instead, they are set at your inlet and the outlet. And the nodes are sequentially numbered starting from node 0, which is our first node, all the way to node n, which is our last node. Remember that this red here denotes that we know some information about this node 0. Either we know the value of y, or we know the slope of y at this point. And the same thing when it comes to node n. We know either the value at this location, or we know slope at this. So that is our boundary value problem. So boundary value problems are different from initial value problems in that our boundary conditions or our known conditions are specified at two different locations as opposed to one location. Usually is the. So in finite difference approach, what we are also doing is we are taking our continuous domain and discretizing it or specifying a set of nodes. And for simplicity, we have specified them to be equidistant. And we are going to make our calculations at these nodes rather than at every point within. Of course, if you want a value somewhere in between, you can interpolate between these two nodes to get an approximate answer as to what what the value of y is at that location. There are three basic forms of finite difference formulations. One's called the forward difference, one's called the backward difference, and called the center. Typically, when we are trying to solve second order ODEs, we make use of the center difference. And here I'm going to show you the formulas of what the forward, backward, and center differences equations are. So if I have my derivative del C over del X, and I want to calculate either the forward, the backward, or the center difference, what I make use of is I'm going to start at my location of interest, and I'm going to call that node I. And then the node that is to the left of it is I minus 1. And the node that is to the right of it, it is I plus 1. So we can look at these three nodes and we write our derivative in terms of the three nodes. So we want to know the derivative at this location I, and we write this either in terms of these two nodes, or these two. The forward differences, the slope or the dc dx is approximated as c of I plus 1 minus c of I divided by delta x, where c is our variable for which we are solving the differential equation, and then delta x is a known value that is known. So this delta x is known to us. We want to keep this as small as possible because we know that del c del x is slope with delta x, the limit of that delta x goes to 0. So clearly this approximation holds if this delta x as small as possible. And in the forward difference, we are going to take the value here, subtract it from the value of I, and then divide it by the delta. Similarly, in the backward difference, we are going to we're going to take this value and then subtract it from Ci minus, divide that by delta. So forward difference means I plus 1 minus C of I divided by delta x. And then backward difference means C of I minus C of I minus 1 divided by delta. Keep in mind that we only know our values of C here, and we may have some information here. We don't have this. So what happens is we are writing the values in terms of two different unknowns, right? Your I plus 1 and I, or I and I minus 1, both of which at this point. Of course, we can take the forward difference, backward difference, and take the average of these two. That way, we can get the slope looking to the left and looking to the right and get an average slope. And that slope is nothing but C of I plus 1 minus C of I minus 1 by 2 delta. So if I add these two terms, what will happen is this negative will turn into a positive, and then C of I minus C of I and plus C of I will get canceled. And of course, I'm dividing it by 2. That's what that took. And this is our first center difference equation for our first derivative, which is d. Now, if we want to write the second derivative and we want to write the central differences, the way we go about doing it is we say d squared c over dx squared, which is the second derivative. We say that's approximately equal to dc dx of I plus 1 minus dc dx of I divided by delta x. So here we are making of the forward difference equation, and we are writing I plus 1. Of course, we can further expand out this dCdx term. And what we do for the I plus 1 term is we're going to write it as the forward difference form, which is C of I plus 1 minus C of I over delta x. And then this minus drops down here. And this del C delta x, we are going to write this in terms of our backward difference. So that is Ci minus Ci minus 1. There's a typo there. It should be I minus 1 over delta x. And this whole thing is now getting divided by this delta x carrying from the above equation. Now, if I simplify this algebra, this delta x goes to the denominator and becomes a square term. I have the Ci plus 1, negative Ci minus the negative Ci will give negative 2I. And then this negative will add up and form Ci minus. So this is our center difference form for our second order equation. So what we did was we started off with a forward difference equation. Of course, wrote one of it as a forward difference, another one as the backward difference, and then came up with algebra. If you started off with the backward differences, you would come to the same conclusion as well. So that's how, of course, you have to write one as backward and one forward, and that's how this operates. So the two important formulas for us are dCdx is equal to Ci plus 1 minus Ci minus 1 divided by 2 delta x. This, if you recall, is strikingly similar to the Euler's equation that we saw with the first order ODE. And then we have del squared C over del x squared is Ci plus 1, 2 of Ci plus Ci minus 1 divided by delta x. So once we have this, we can go back to our equation. The equation that we are going to be looking here is called the Advection-Dispersion-Reaction equation, or the dispersion-advection-reaction equation. We have here a dispersion term, and D is the dispersion coefficient. This is the second order, ODE, the concentration, minus this is the advection term, and this is the reaction term, and this is kind of first order derivative here. The dispersion essentially is the mixing that is taking place in your system, because as water moves through the system, different parcels of water are actually moving at different velocities, and there is also molecular diffusion or movement of chemicals from high concentrations to low concentrations that adds to this mixing and causes the movement of pollutant. And that's what this dispersion term captures. The advection term essentially denotes the movement of the pollutant due to the movement of water or air or whatever the solvent in which that pollutant is present. And then this Kc term is a measure of the reactions that are taking place in the system, and we are going to assume that they follow first order kinetics or some sort of an exponential decay, and that gives us minus. As you can see, if I know this D, I know V, and I know K, this is actually a homogeneous first order ODE. But keep in mind that our in the conditions are not given at the initial condition, and we don't have two conditions both at the inlet. We have one condition at the outlet. So the A and B, if we were to solve this analytically, would correspond to two different locations. So now that we have this equation, and we also know how to write our first order and second order terms in terms of our difference equations, what we can do is we can plug in the finite difference forms for our d squared cdx dcd terms, and that's what's happening here. What we're doing here is we are taking the dcd term, d squared cdx square term, and kc term at some generic node I, and then plug them all into this. When I do that, I will be writing an equation. This will eventually become one equation which will have an I minus term, an I term, and I plus 1. And I can move this stencil of I minus 1, I, and I plus 1 with starting from this point. I already know the concentration here. So I will start here, and then I'll have these three terms. Then I move here, the stencil terms. Then I move here, and then the stencil here, this, so on and so forth. So I can take this I minus 1, I, and I plus 1, and essentially put it here, I is equal to 1, and then move it all the way till I is equal to n minus 1, because I know something about I is equal, the concentration at I is equal. So essentially, those are how I'm getting the two derivative terms. And then when I plug everything, this is the equation I'm going to at some generic node I. And remember, it's got an I plus 1 term as well as an I minus 1 term. And it also has. So when I collect all similar terms, I can write d over delta x squared plus v over x c of I1 plus minus 2d over delta x squared minus k ci plus d over delta x squared minus v over 2 I plus 1. So I have an I minus 1 term, I term, and I plus 1 term. And essentially all I've done is, moved or collected terms. And again, this has to be an I minus 1 term and as shown. So I can take these parenthetical terms, d over delta x squared plus v over 2 delta x. I know this value. So I know d, I know delta x, which I'm assuming. I know v, the velocity, and then the delta x. So I can essentially compute this once and call that a. I can similarly compute this parenthetical term here, call it b. And I'm going to compute this parenthetical term and call it f. And then when I do that, all I'm doing is writing a of c I minus 1 plus b I plus f of I 0. And then I'm applying this stencil starting from I is equal to 1 all the way one node at a time. So I keep moving from node 1, have these terms, go to node 2, then node 3, 4. So in addition to the node I'm at, the two nearest neighbors, one to the left and one to the right, are also involved in that. So for example, at node 1, which is this node here, I can write a c I minus 1 plus I plus f c I plus 0, but I do know my concentration C naught, that is one of the initial. So I can write a c naught plus b 0. And since this AC naught is a known term, I'm going to move it to the right-hand side. In other words, I'm going to subtract AC naught both sides, and I'm going to end up BC FC. This is what's happening. Now, from node 2 to node n minus 2, that is from this node all the way to this node, I'm going to write AC I minus 1 plus BC I plus FC 1. And similarly, I put I is equal to 2. This will be 1. This will be 3. When I becomes 3, this will become 2, 3, 4, so on and so forth. I can loop through each of these terms and write these. When I go to this last node n minus 1, I'm going to write AC n minus 2 plus BC minus 1 plus FCN here. But if I say that my flux term or that dCdx term is equal to 0 at this outlet boundary condition, then dCdx is equal to 0. So Cn minus Cn minus 1 divided by delta x is equal to 0. I'm simply using forward difference form here, and I'm going to get Cn is equal to 1. So I can substitute Cn minus 1 here, A, Cn. So at node 0, I have this equation. At node 1, I have this equation, BC naught is equal to 0. And from I is equal to 2 to n minus 2, I have this equation. And then at I is equal to n minus, I have this equation. So the first element unknown, which is I is equal to 1, and then the last unknown, which is I is equal to n1, have two elements, two terms, because there's something about this is known, something about this is known, so that gets taken into account. And then the rest of the nodes will have three elements, both the neighbors that are in there. Now, if I write this as a system of equations, for the first term is BC1, FC2. I don't have C3, C4, C5. I don't have values for any of the nodes. So all that gets to 0, and I get not. When I go to node 2, I get AC1, BC2, FC3. Then none of the other nodes are involved, so they're all zeros. That is equal to 0. And similarly, I can go to node 3 and write BC3, AC2, FC4. Yeah. Similarly, when I come to n minus 2 node, I have AC n minus 3 plus BC plus FC 1. And then for n minus 1 node, I combine that B plus FC n minus 1 because C n minus 1 is equal to Cn. I'm using that to combine these two. So this system of equations, there are some coefficients, A, F, B, and then there are unknowns, C1, C2, C3, C4, Cn minus 1. And then I have the right-hand side, which is AC naught, rest are all C. I can write this in the matrix form with essentially A, B, and F. The first one will have B and F, F, A, B, F. ABF will keep moving. And of course, the last term, F. And then my unknowns are C1, C2, C3, C4, Cn minus 1. And then on this side, I have minus A naught and everything else. As you can see, there is the diagonal element, and then there is the left diagonal, right diagonal, two off diagonals. So this is what is known as a tridiagonal matrix. It's also called a sparse matrix because the terms are only there along the three diagonal terms. Everything else is. But nonetheless, this is your coefficient matrix. This is your unknowns. You have n minus 1 unknowns. And of course, if you know n minus 1, you will automatically n is equal to. And then similarly, you know your AC naught already. So that's known. So you can essentially invert this matrix and multiply it with this to calculate these unknowns. And of course, since this is a fairly large matrix, it's better to make use of a computer. So Python offers several methods to solve systems of linear equations. SciPy and NumPy have a module called linal, which stands for linear algebra, and both have a function called solve that helps us solve these equations. So SciPy is preferred because SciPy makes use of slightly modern, backend than NumPy does. So that's why we prefer SciPy here, and we'll be using SciPy here. We can solve a fairly large number of linear equations in the order of hundreds of unknowns by using this. So one of the advantages is that once you understand finite difference equations and how they can be applied, you've essentially converted your differential equation, your boundary value differential equation, into a system of ordinary differential, a system of algebraic equations or a linear system of algebraic equations. Solve it using Python. So I'm going to illustrate an example to kind of tie all these concepts together. And in our illustrative example, we are going to look at a wastewater treatment plant from a small community that discharges treated wastewater into a creek. The creek is 10 kilometers long and on average 2 meters wide. So it's a fairly long, thin, creek. And the concentration of biochemical oxygen demand, which is a measure of the organic waste in municipal wastewater at the discharge point, is 30 milligrams per liter. So typically in a household waste, the biochemical oxygen demand will be in the order of 100 to 200 milligrams per liter. And and then the average velocity here is essentially um, um, below the discharge point is 50 meters per hour, and the dispersion coefficient is estimated 13,050 meters square per hour. So those are your two input parameters: velocity, which is equal to 50.4, and the dispersion coefficient, 1,003 per hour. The degradation rate is estimated to be 0.005 per hour. And we want to draw the BOD concentration profile over the stream length. We are going to assume no flux outflow boundary. So our conceptual model, we have a concentration of 30 milligrams per liter inlet, which corresponds to our node 0. And then we have dCdx, which is our flux boundary condition, which corresponds to I is equal to n. The length of the river is 10 kilometers. And since the width is fairly small compared to the length, we essentially are going to treat this as a one-dimensional river. And we have node 1, node 2, 3, which are all at a distance delta x. Delta x is something we have to assume. So we are given a stream length of 10,000 meters, which is 10 kilometers. We have the average velocity, which is 50.4 meters per hour. We have the dispersion coefficient, that is 13,350 per hour. The degradation rate is 0.003 per hour. Delta X is 25 meters. This I've assumed. And the inlet concentration is given to us as 30 milligrams per liter, which is the same as. The one thing that we have to make sure is we are dimensionally consistent. And here I'm going to use meters for length. And then I am going to use hours, my units of time, and grams for. So I'm going to use grams and hours for length, for mass, length, and time, respectively. So again, I calculate my A, B, and F, which are the three constants that are based on the dispersion coefficient, my velocity, my first order degradation rate, and my chosen time step or space step, delta x. And I write my equation. This is my matrix coefficients. These are my matrix of unknowns. And this is my of the right-hand side, of which I only know one term. The rest are all easy. So this is the code. So first I do is I import libraries. I've imported NumPy, and I've also imported SciPy, linal. From this SciPy, I've imported one function called solve. And my model inputs are my velocity, my dispersion coefficient, k. I've slightly changed this k here. I was playing with, and then C naught, L, and x. Of course, you can change any of these numbers to see how your model reacts. And then the next thing I do is I take these values, calculate A, B, and F. And then the number of nodes is equal to the length divided by delta x1. And this has to be an integer, so I convert that into. Remember that the number of nodes, you have a node at 0, which is why you get this here. Goes all the way. So what I then do is create a coefficient matrix, and I'm creating a coefficient matrix comprising of n minus 2, n minus 2, which is I'm creating an n minus 1 by n minus 1 matrix, because that are the number of unknowns. But since my values start at 0, I'm using n minus times n 2. So that is the matrix that I'm creating. And I'm creating a sequence of node numbers using 1 to m plus 1. Remember, m is n minus 2, so I want to go all the way from n minus 1 at increments of 1. So this is what this is doing. It creates a range of indices. Then I'm going to loop through each of these nodes. And if I say that at node I, my I minus 1 is B, and then I F, remember these are in columns, my rows stay the same. And then else I go into my, or if I is equal to n minus 2, what I do is I use my coefficient that goes from I minus 1 to I minus 2, and then I minus 1, I minus. So essentially, I'm calculating the last two elements here. All dimensions will be off by 1 because in Python we start at 0 instead of starting at 1. So, if you add 1, it will start seeing that I'm writing this at 1, and this will be at I minus I. So that's kind of what this is. And if these two conditions, if they're not the inlet and the outlet node, then I calculate my ABF for I minus 2, I minus I, which, is basically I minus 1 from what I've been. So let's print this. And the printing is to see if the coefficients are tridiagonal. And then I get my right-hand side matrix, which is nothing but a set of zeros. And I'm replacing my first element or the first row and the first column to be A of C as being equal to minus A of C naught. Everything else. And then all it takes is one line of code. I've already imported this solve, and that solve was imported from scipy.linalg. So from that module, I brought in solve, and then I use solve. I give the coefficient matrix, I give the right-hand side matrix, and I get a constant. Once I get the concentrations, what I do is I want to put that data in proper format. So what I'm doing is I'm getting my x values from delta x to L, increments of delta x. I'm going to flatten it, take it to a list, and I'm going to insert x is 0 at the first point, and then I'm going to flatten that again. And similarly, I take c of x, turn that into a list, flatten it and list, and then I add 30 for the first column, my known inlet concentration. Once I have all the values put in, then I call matplotlib and then make my plot, plotting x versus x. And then I'm adding the labels, a grid, a legend, and a title that is saying BOD concentration downstream point. And then finally, I'm asking to show the matrix. And voila, the result looks like this. I'm starting off at 30 milligrams per liter at x is equal to 0. And as I move down, the concentrations of the pollutants start to taper off and decay. And when I hit the 10,000 mark or the 10-kilometer mark, the concentration slightly above 5 or so. So there could be some limitation that says that, what is the distance before a next treatment plant can put in. So we have to make sure that this concentration goes sufficiently low before the next city gets its opportunity to discharge waste. Otherwise, we adding waste too quickly, that will in turn cause fouling of the river and BOD accumulation, other problems. So models like this are useful to do what are known as waste load allocations, which basically city how much waste they can discharge into a river and where should they be discharging waste at what location, so on and so forth, so that the impact on the environment. So At the end of this lecture, you should know what boundary value problems are. These are essentially differential equations where your conditions, known conditions, are given one at the beginning, one at the end. You need to know what finite differences are. This is a way of taking your differential equation derivative and turning it into an algebraic expression, very similar to the Euler's method or the Runge-Kutta method that we saw when solving first order equations. And then we saw how to write finite difference equations for steady state problems or ordinary differential equations, and then the matrix formulation associated with it. And then finally, we saw how to solve system of linear equations in Python.